Hello, this is a list of nodes which we are going to discover along this lesson, as well as we will use the nodes that we already know from the last two lessons. Okay, let's get started. This time we will use a torus. Let's jump into it. Put a 300 for rows. 600 for columns. Let's drop down the attribute VOP. Connect the torus. And jump inside. Let's expand the workspace. We can minimize this shelf to expand the workspace even more. Let's also minimize the timeline. Now let's create a displace along a normal node. This operator displaces the surface along the surface normal by a given amount. Plug the displace position to output P. Look, by changing the displacement amount, the geometry is displaced along its normals. Now I propose to drive the displacement amount by the noise. For that, let's drop down the turbulent noise. Connect position to it, then connect 1D output to the amount. Look, the torus has displaced by given noise. We can also scale the displacement amount. This is a simple multiplier, that's why the negative values invert the displacement direction. I also want to change the noise type. Select the original Perlin noise. Then adjust the noise settings. Okay, it's good for me. Now I want to introduce you to the maximum and the minimum operators. First, let's create the maximum. This operator outputs the maximum value from its inputs. Let's plug the noise. Then create a constant value for the second input. The output goes to the amount. Look, the maximum node compares the incoming values and chooses only the highest values from them. Since we compared the noise values to 0, the maximum node chose 0 instead of negative values, therefore in some areas of the torus, the displacement is equal to 0. Let's tweak the value of the second input. As you can see, by increasing this value, noise gradually disappears because the noise value becomes less than this value, or vice versa. There is also a minimum node, let's create it. This operator outputs the minimum value from its inputs. Let's plug the noise. Then plug the constant. And the output goes to the amount. As you already noticed, the exact opposite turned out because the minimum node selects only lowest values. Let's play with constant value again. Great, let's go on. For comparing these two nodes, we can use a switch node. Let's create it. This node switches between network branches based on the value of an input. First input is an integer that specifies which input to pass through to the node's output. The numbering starts at 0. Now let's connect the inputs between which we are going to switch. Switch output goes to the amount. Look, now we are switching between the two versions. When the index is 0, the input 1 goes through the switch node, when the index is 1, the input 2 goes through the switch node, and so on. Let's also plug the third version, which is simply the noise. Here we go, we can switch between three versions. Now I want to promote the switcher index at the object level. For that, let's create a parameter node. This operator creates a parameter of any vex data type and promotes at the object level. Now let's jump at the object level. Here it is, newly created parameter. Let's dive inside again. Like a constant node, we can specify all vex data types. The parameter type must be an integer. I will call it switcher. Connect this parameter to a switcher. Now let's jump at the object level and test the switcher. Excellent, we can move on. I also want to show you the shortest way to create a parameter node. First, let's delete this one. Then right-click on this port, and instead of a constant we will choose the Promote Parameter option. Look here, it is created, but it shows up as a small icon because it is in a hidden state by default. In order to see it as a separate node, just double-click on it. To hide back, just right-click on it, select the flags, then click on the Hide node. Let's check again if everything works. Great, let's go ahead. Now I want to colorize the torus, taking into account the degree of deformation compared to the original shape. For that, let's create a subtract node. The displaced position goes to the first input, the original position goes to the second input. Subtracting these two positions, we get the difference between them. Let's plug the result of subtraction to the output position. This is a difference vector between two shapes. Okay, let's connect back the displaced position. Now we need to get the length of the difference vector. For that, let's create a length node. This operator computes the length of a 3D or 4D vector. Plug the difference vector. For coloring, we will use the ramp parameters node. Let's create it. Make sure that ramp type is specified as a color ramp. Plug the length of the difference vector. The output of the color ramp goes to the CD port. CD attribute is just a color diffuse of each point. Look, our geometry is now black and white because by default the color ramp creates a gradient between black and white. To have a bright white color, we need to fit the incoming range. Let's create a fit range node. We need to adjust only the source max. Now let's jump at the object level and set up the ramp colors. This is good for now. Let's jump inside again. I want to adjust a source max again. Take a look, areas where the deformation length is 0 or tends to 0 are colored blue, and areas where the deformation length is maximum or closer to the maximum are colored red. Great, now I want to introduce you to a new node that can replace these two nodes. It is a distance node. This operator returns the distance between 2 points. In simple words, the node subtracts two vectors, then calculates the length of the difference vector. Let's connect both positions. Then plug the length to the fit node. Here we go, the result is the same. Let's get rid of these two nodes, we don't need them anymore. Now I want to show you a new node called mix. This operator computes a blend, or a mix, of its input values using linear interpolation. If the bias specified is outside the range 0 to 1, the values will be extrapolated linearly. Now let's connect both positions to it. We can temporarily delete these connections. The output of mix goes to P. Now let's play with bias. The mix node blend these two shapes. When the bias is 0, only the first shape is visible, and when the bias is 1, only the second shape is visible. In between, we get a mixed shape. Let's also override this connection by the mix output. Now we can return the colors. Let's play with bias again. Here we go, the colors are also changing. Now I propose to derive the bias with some mask. For making a mask, I will use the bounding box information. Let's type a bound and drop down a relative to the bounding box node. This operator returns the relative position of the point given with respect to the bounding box of the specified geometry. First, we have to specify in which geometry to look for the bounding box information. In our case it is the same geometry, so we will connect op input 1 to the file. Look, these 4 strings represent these 4 inputs of the attribute VOP. The first string always represents the geometry itself. Okay, we also have to give a position vector. Now we can use the relative bounding box information as a mask. Let's create a vector to float node. Connect this vector. The X component goes directly to the CD port just to visualize the mask. Look, we have a mask ranging from 0 to 1, and the mask grows along the X-axis. We can also use a mask along the Y-axis or Z-axis. To make it visually more obvious, let's create a set vector component. Connect this to the float input. The output vector to CD. Look, the mask turned red because we only connected to the first component, which is the red channel. Now let's check the masks in all directions. Okay, let's move on. In order to reverse the mask direction, you can use the complement node. Let's create it. This operator computes the complement of the argument by subtracting the argument from 1. Since the range of these masks is between 0 and 1, the complement operation reverses the mask. Okay, now let's use this mask. Move these nodes closer to the mix node. Plug the mask to the mix bias. As you can see, the noise gradually disappeared along the opposite direction of the X-axis. Let's disconnect the mask visualization. Then wire back the initial color. Okay, now let's decide in which direction to fade the noise. Let's choose along the Y-axis for now. Look, there is no noise at the bottom of the torus. We can also fit the range of the mask. Create a fit range node. Wire to this line. Playing with source max and source min, we can adjust the mask as we like. Now let's try to animate this mask. For that we need an add node, let's create it. Connect to this line, then promote the second input. Let's jump at the object level. Here is our promoted parameter. Okay, let's jump inside again. Select the parameter and put a -1 for the minimum value. Let's jump up again and tweak the parameter value. As you see, the noise disappears and reappears along the Y-axis. Now let's change the fade direction. This time I will choose along X. That's it. Everything works as it should. Okay, let's go on. The last thing I'm going to do is control the fade mask by spline ramp. Let's create it. We have to rename it because the default name already exists. The ramp type will be a spline ramp. Give it an input, then connect output to bias. Now we can jump up at the object level and set up the spline ramp. Let's check what we have now. It seems we need to reverse the spline ramp. Here we go, that's what I was looking for. We can also change the interpolation type. Let's check again. Excellent, it's the final result. The last thing I want to do is change the fade mask along the Y-axis. Let's see what it looks like. Nice, I think we can stop there. In the next lesson we are going to discover a lot of new nodes and we will delve even further into the VOP context. See you in the next lesson.